All right, thank you. It's a fantastic honor to be kicking off this conference, and by doing so, by giving a talk that will tell you a little bit about all the amazing, my goal is to set up other talks in this session, which are going to tell us about all the amazing results that have come out over the past year and a bit, describing what the success of gravitational wave observations has already taught us about black holes and where we expect to see these things going. I take an enormous amount of personal inspiration when I think about black holes and doing research in black holes from this wonderful quote by Chandrasekhar, which I think actually could be carved into the stone on the BHI and the Black Hole Initiative building. In my entire scientific life, extending over 45 years, the most shattering experience has been the realization that an exact solution of Einstein's equation of general relativity provides, and I love this line, the absolutely exact representation of untold numbers of black holes that populate the universe. You know, that is, bear in mind, this was said in 1975. You read that and you think, man, this is really cool. And you also think, this is a guy who's got some chutzpah. I mean, this is someone who's really got confidence in the mathematical description of black holes and what goes into the extent to which the theories are going to describe the data that we can later measure. About a decade later, he revised that a little bit when he pointed out that, you know, although it's well known this provides the unique solution for stationary black holes in the universe, a confirmation of the metric of the Kerr spacetime or some aspect of it cannot even be contemplated in the foreseeable future. Well, that was a little over 30 years ago that he came out with that statement. In this future, not only can we contemplate it, we're starting to do it. And that's what I want to talk about, at least from the standpoint of gravitational waves, and hopefully others in this talk, in this session will continue on that. So, if you want to talk about black holes and gravitational waves from a certain perspective, it can't get much simpler than this. You write down the vacuum Einstein equations, figure out what your initial data is, and go. Literally, that's all it is. Okay, and this is indeed something that we can now go ahead and solve for a lot of very interesting and important astrophysical configurations after several decades of sort of banging our head against the wall to actually make these things work. And you'll hear a lot more about that, I believe, in Deirdre Shoemaker's talk. What comes out of this analysis, and here's what I want to do, is try to give an idea of how the information that describes black holes is imprinted in the gravitational waves, is that the imprint of two black holes' orbital dynamics about one another is imprinted on those waveforms. In particular, the phase follows the kinematics of the bodies in these binaries. And to give you some intuition, I'm going to just step you through the simplest calculation you can do. So if I use Newtonian gravity, I consider two bodies in circular orbit, write down the energy associated with the Newtonian orbit, orbital frequency, and then I just add to this the energy that is lost by the lowest order contribution of gravitational waves. What you find is that the bodies slowly spiral towards one another with the phase chirping up, with the frequency chirping up as time passes and the bodies get closer and closer together. And what you discover when you do this analysis is that the rate at which this frequency sweeps up is governed by a single combination of the two masses of the black holes in this binary. It's a combination we call the chirp mass, for obvious reasons, which is essentially just a simple function of the two black holes' masses. And that's it. That's the only thing that enters at this level of analysis. And so you measure this frequency rate, you measure this frequency sweep, you measure the mass. Okay? So that's one bit of information that's very accurately carried through there. Now, it's worth emphasizing that when I did that analysis, I only used Newtonian gravity. And so you can think of that as a force law that is indeed what you guys, what we've all learned in freshman physics. And in general relativity, this is, of course, just the first term in a much more complicated description of gravity. And as the bodies get closer together, we find we have to correct Newtonian gravity. And that introduces additional things that I won't go through. But the key point is that it gives me new dependencies on the mass that enter into the motion and that therefore imprint themselves on the gravitational waves. And so I can measure more than just that chirp mass. There's additional things that come in and have an effect. Okay? And if you like, you can go a little bit further and include some other terms and a couple others. Those of you who would like to check Luke's algebra, here's the reference. But the key point is that this is it's something that follows in a very natural way from the theory of general relativity. But there's more to this. One of the things which I think is a fun one to look at is that in general relativity, all forms of energy gravitate. In particular, the energy bound up in a body's spin generates a form of gravitation. And what we find is that if your two black holes in your binary are spinning, those spins precess due to a magnetic-like interaction between this one body's spin and the other body's spin, and one body spin in the orbital angular momentum. And what this does is it causes, you can see that the two spin vectors are precessing a little bit, and if you crack out your freshman physics, you'll see that this has exactly the form that you would expect for a magnetic dipole sitting in a magnetic field. It looks just like that. But there's a rule that angular momentum must be globally conserved, and so what happens is the orbital plane has to precess in order that this sum remain constant. And when you ask, what does that actually do to the bodies? So I'm showing you here is what the two black holes precessing look like. Here's the orbital plane. You can see the orbital plane precessing around in such a way as to preserve the constancy, that's what that green vector here is, of those two, the sum of the angular momentum in this system. So this, again, becomes a kind of information that is imprinted onto the gravitational waveform that we hope to be able to measure and then to use this to learn about spins. And we'll hear a little bit more about that in some of the talks that follow. You can see very clearly the imprint on the amplitude. There's also an imprint on the phase, which is a little harder to see in this picture, but trust us, it's there. When the system comes together and these two black holes coalesce, you get a fascinating phenomenon, which I think is actually, one thing which I really like about it is there's a strong similarity between one way of thinking about the physics of this and some of the physics that describes what we want to measure with the Event Horizon Telescope. So as the system settles down, there will be some waves generated throughout the coalescence process which are trapped on the light ring of that final black hole and gradually leaks out with such a form that it comes out as a damped sinusoid. And what we get out of that thing is that this whole signal ends with a little ring down in which this thing sort of rings like a bell as it settles down to a final Kerr black hole. It's a fairly lousy bell. Okay, this is a bell whose quality is measured it's of order 10 rather than a couple hundreds or thousands or something like that. But nonetheless, this thing does ring like a bell. Now, one thing which is really fun about all this is that general relativity has no intrinsic scale. So everything I just told you, whether those two black holes are 10 solar masses, 10,000 solar masses, or 10 billion solar masses, it all holds. Where it enters into our physics of what we can observe is that the frequencies are determined, the frequencies of the signal that we try to measure are characterized by that mass scale. And in particular, they go inversely with the masses. And so with a little bit of slop that depends on factors like orbital geometry and black hole spins and things like that, we find that they are all confined to some numerical values that are simply related to 1 over GMC cubed, where GMC cubed is sort of a fundamental time scale of a black hole. When we plug in masses that are on the order of tens to hundreds of solar masses, these waves come out at hundreds to tens of hertz, right smack in the band of LIGO. We're going to hear a lot more about that in the talks that follow. Dial that up to, say, 10,000 to 10 million solar masses, and the frequencies come out at sort of centered on the millihertz band. This is exactly the kind of range of frequency that is being targeted by the LISA constellation that is under development, thank goodness, once again, and that we all hope will be launching at some point, before I retire would be nice, but at some point in our lives. And then finally, I'm not going to say too much about this, but if we make 100 million solar masses up to about 10 billion solar masses, the gravitational waves come out in the nanohertz regime. And this is something where people are even now beginning to place constraints on this background by making very precise measurements of signals from widely separated millisecond pulsars on the sky. So what do we get out of these things? So first I want to think about this from an astronomy point of view. We've already essentially had one surprise. Okay, we're going to begin taking a census of black holes and their properties, and right away the first discovery showed us that there are stellar mass black holes larger than have been observed by any other mechanism that not only exist, but form binaries that can merge in less than the age of the universe. As we move forward, I think the really exciting thing to think about, and you'll hear more about this, I believe, from Daniel Holz and Matt Evans, is what happens as we make our detectors more sensitive. If you take this noise curve and you push the low frequency noise down, so this is what these signals look like in the frequency domain, you pick up more and more of that early in-spiral signal, gives you better precision on the masses and the spins, gives you a better ability to do things like localize these events on the sky. Push down that high frequency noise, and you're going to get much better information about that late merger and ring down signal. We'll be able to make much better information about the mass and spin of the final remnant, and do things like measure. There's actually a whole bunch of modes that in principle should be present there, and we can measure more than one of them if we can measure these things. There's good stuff we can do with that, and I believe Emanuele Berti will say a thing or two about that in his talk. going to some of the more, thinking about what we can do with LISA, part of what's sort of beautiful about this is it can measure the mergers of black holes out to redshifts that are, kind of insane, redshift 15, 20, and things like this. And so this turns us into a tool for tracking the growth of massive black holes over early cosmic times. LISA will also be one of the ones which is exciting to me in particular and some others. You can measure capture processes where you have a small body getting onto a relativistic orbit of a black hole in a galactic center. It's kind of like what goes into a tidal disruption event, but think of the body that's going in as a black hole rather than a star that can be disrupted. And so these are things where you get a couple tens of thousands of orbits that allow us to probe the black hole's properties with high precision. There's also great physics we can do with these things, okay? We've already seen some of that, but let me just point out a couple of the ones that I think are particularly interesting where we can begin doing things like testing the nature of black hole spacetimes and really, finally, looking at that future that Chandra did not see in 1986. So one example of the kind of thing you can imagine doing is ring-down spectroscopy. So if you have a mixture of lots of different modes coming at the end of black hole coalescence, general relativity demands that each mode have a particular damping time and frequency. If you measure a spectrum of those things, you have a consistency test. Boom, go in there, you test whether general relativity's got it or not. Another one is that Kerr black holes have a particular shape associated with their spacetime, which we can characterize by a spectrum of multipole moments. By the no-hair theorem of classical general relativity, only two of those moments should be independent from one another. They characterize the object's total mass and its total spin. You measure more than two of those things, boom, you've got a consistency test for the no-hair theorem that allows you to test the structure of the Kerr metric. So this was a fairly rapid and somewhat breathless walk through all these. Oops, as I said, consistency test. And a lot of other details will now be left to the speakers that follow me. Actually, just about done. And so the main thing which I want to take away is that we've already got some amazing things that have come, that have been found, and it's just getting better. So we'll be probing space-time dynamics with this great astronomy and great physics. And apparently I ended a little early, so we should have time for questions. Thank you.
So you talked about the ring-down spectrum, the different frequencies. Yeah. What about the phase relationships, if any, among the different modes? Is that totally free, or is that also constrained in any way?
Well, strictly speaking, each mode is so to the extent to which the ring downs, they are done by looking at sort of linearized perturbations on this thing, and when you're in the linearized regime, each mode is completely independent. But of course, that linearized regime emerges from a complicated nonlinear regime that preceded it. And so whatever is the dynamics that went into setting up this final state, that should inform what the phase of these modes are and what the relationship between all of these things are. And so you can imagine formulating this kind of test in a couple of different ways. If you really just look at the last couple cycles that are coming off of this thing, you're sort of agnostic about those phases, and you go in and you just measure them and you check to see whether their damping times and ringing frequencies are consistent. But you can imagine doing a numerical simulation of the kind of thing that would set up this late stage thing, and then that should make a prediction for what these things are. So I think there's a couple different tests you can imagine formulating to do that. Again, I don't know if Emmanuel is going to say something to speak to that, but that's the kind of thing you've done more on that than I have.
Eric?
So you mentioned that you are at the end that you can use the no-hair theorem to characterize that you can use the no-hair theorem to characterize the black holes. But the no-hair theorem, strictly speaking, isn't applicable to a binary system. It's not stationary. I'm curious, how do you characterize the deviations for the no-hair theorem?
Right, so for a situation like this, we're imagining a case where it's one of these systems that's kind of like the analog of a tidal disruption event, where you have a stellar mass black hole captured onto the orbit, a strong field orbit of a black hole at the center of a galaxy. So there's a very large mass ratio in that system. And when you go through and you analyze that, you certainly have a little bit of a correction, but the system is dominated by the space-time of the large black hole. And no-hair theorem does describe that. You then have a perturbation that pushes you away from that somewhat. But the dynamics of that inspiraling body are governed at the level of part in 10 to the 5 by the space-time of the larger body. And so you certainly have a correction that arises from the second member of the binary. But you are close to, it's the kind of thing where you're close to a stationary exact solution, and so your measurements probe that stationary exact solution.
So you're certain that the future is bright here. To what extent do some of these tests depend on the populations you expect from LIGO and LISA?
So in case it didn't come through, so Shep is asking, to what extent do these tests depend on the populations? All of them, right? I mean, if there's no black holes, no binaries, there ain't no test. But so far what we have seen is for the kind of things we're measuring with LIGO, we're going to hear more about this to the extent that confidentiality clauses permit, that the rate appears to be quite high in the stellar mass band for these things. And so, unless there were sort of 2.87 events last year and there's been nothing ever since, we're assuming at this point we're going to be getting multiple events per month sort of moving forward. Going into the LISA case, there's a lot of uncertainty as to how to model, for instance, these extreme mass ratio captures, but we know the big black holes exist. There's open questions as to how often do you get a stellar mass black hole scattered onto its strong field orbit. But this is a very similar dynamical process to what creates tidal disruption events. So we're pretty confident that these kind of things, it's typical kind of stuff when you model this. There's uncertainties that are in the exponents, but the low end suggests tens of events per year, the high end suggests thousands of events per year. For other ones, we're looking at the mergers of black holes at high redshift. We don't have a lot of evidence telling us exactly how often that occurs, but we see black holes back to redshifts greater than 6. We see galaxies merging. Something has to bring them together so that we have what we observe in the local universe today. So, although there is, there's uncertainty and there are issues that you might be concerned about, wonder what specifically the numbers are, I'm not concerned the numbers are 0, okay? The question is, in some of these cases, we're actually a little more worried they might be too high because you might end up with sort of a confusion limit entering, and you can't do these science tests if there's too many sources to detangle.
How far are we from being actually be able to measure this ring-down spectrum? What are the prospects?
The initial LIGO event, let me just go back to show you, there we go. So you can kind of see for the initial discovery event where its sort of last waves come with respect to the noise curve, okay? So that one, when you actually look at the signal, that one we basically measured it, or at least we showed consistency with the ring down. If you just look at the ring down on its own, and that, it's consistent with the first quasi-normal mode being present, I think is the correct thing to say. It's not something, it's detected with a significance, that little piece of the waveform alone with a significance of 2-ish sigma, something like that. And so what needs to be done to measure that with higher significance is lowering the noise floor, more events, maybe an event where the peak sensitivity moves to lower frequencies. Okay, it's something that could happen today or tomorrow, I would say, is beginning to get information about that.
And that testing the multipole spectrum, is that something that might be done in the next decade?
So so testing the spectrum of quasi-normal modes will certainly, I'm going to leave that for Emanuele Berti, that's his talk. I will leave something for your talk, Emanuele. This idea of measuring the shape of the curve spectrum, that's a project for future LISA measurements. And so that's, I wasn't joking where I was saying I hope it flies before I retire, but I'm confident it'll fly before I die. So.
Okay. Quick.
Yes, quick question. A while ago, you and the second speaker, Dan Holz, wrote a paper where you argue that perhaps standard sirens would be useful for cosmology, but now that cosmologists have the parameters pinned down to the level of a few %, do you think it will be useful for that purpose, or do you see just taking the cosmological parameters and using these sirens for something else?
Yeah, I'd say this has definitely evolved. Daniel, are you going to talk about this in your talk?
I wasn't.
Okay, well, let me just make a remark, and then you can go on that a little further if you like. So the basic idea here, for those who aren't experts, is the gravitational waves directly encode luminosity distance to the source, but give you no information about redshift. And so it's kind of the converse of the usual system in astronomy, where you can measure redshift from a spectrum, but you don't get any information about distance. So if you can get both an electromagnetic counterpart and a gravitational wave spectrum, gravitational wave information, you can get both distance and redshift for a single event. And as you say, we were very excited about the possibilities that this would have for interesting cosmological measurements, but time has moved on, and I think a lot of that has perhaps been swept out from under us. Now, one thing, though, is that this is something where it's very different systematics from a lot of other measurements. And I think it would be very interesting to have another technique in the bag that would allow us to check whether the Hubble constant is 66 or 72, for example, since we are seeing tensions between different techniques that do things like that. Beyond that, I think one of the most useful things that can come out of this then is when you measure the distance, even if you don't get a redshift, we know the cosmology well enough now that you can invert that to get a redshift relationship, and various degeneracies between redshift and other parameters can be broken. You can immediately learn rest frame masses and spins and things like that.
Okay. Thank you, Scott.
Okay, so it's really great to be here. It's great that the BHI exists. The timing is impeccable for an institute like this. And I'm really looking forward to a couple of interesting days. So my job is to give the overview of the LIGO results. Scott really gave a perfect background to what I'll be talking about. I would like to, actually, let me just comment on the standard siren thing, just since. So I just want to emphasize 2 points that Scott made. So the first is independent is really important, because systematics is the whole game here. If you want to falsify dark energy, you really have to know what you're doing. So falsify particular cosmological constant. But the other point I'll make, and I think this really is something that's going on right now, is there is this controversy, and it seems to be becoming more severe as time goes on in different ways of measuring the H0. And so right now it's maybe 3 sigma or 4 sigma, depending on who you talk to, and the camps are solidifying. So this is basically low Z measurements using supernovae, high Z using CMB, and there's just a very profound discrepancy. And this is exactly the sort of thing that standard sirens can kind of come in and inform. So I think there's still, surprisingly, we should be out of business, but surprisingly there's actually, it's good motivation for this sort of thing. Okay, so let me start by showing this. I think, all LIGO speakers are required to show this plot. LIGO is absolutely amazing. I'm sure Matt will talk more about this, but let me just remind you that this number is completely insane and shouldn't be possible. But there it is, and here's our noise curve. Okay, so this should totally blow your mind. Also, that first event is totally awesome. I still can't believe the data is so beautiful and everything fits so perfectly. So I'll talk a lot more about that. So I'm just going to give you the very quick summary of where we're at. So LIGO had its first science run, 01. We had about 50 days of data. We had roughly 2.9 events, and we had a bunch of papers, and I'm going to kind of summarize a lot of the results from that. We are now operating, at least for a couple more hours, in 02. We started right at the end of November. The plan is to go until late August. We've issued some alerts. We haven't said anything public about this data set yet. And I'm not going to change that in this talk. And my guess is Matt won't either, and neither will Deirdre. No. Okay, so, and we're about to turn off for a couple weeks. Hopefully things go smoothly, and then we'll be back on. All right, and the short version is we had 2.9, interesting sources. We had, of course, the main event, 150914, and then we had a candidate event about a month later. This, we don't call a real event, it's just the SNR wasn't quite high enough, the false alarm rate. It's just not good enough for us to be confident. And then right on Christmas Day in the US, we had our third event. And This is a version of a plot that Scott showed, but I think it kind of crystallizes what we've seen so far within LIGO, and what, there are a few things going on here. This just shows when you can think of it as when they come into band. These are the actual waveforms we get, and you notice that the first event was very loud. The amplitude is high here. The third event, the second detection, is much lower SNR, but there are many, many more cycles. And so you can integrate up, and there's enough SNR here for us to be confident. This one is kind of in between. You also get a sense of the frequencies, and as Scott mentioned, the frequency is directly related to the masses. Low frequency here means higher mass. This is the lower mass event, many more cycles. Okay. So that's what we've detected. So let me just now go through just a few of the things we've learned from these events. Okay. And I think this is really a stunning plot. So this is the whitened data. So you can think of it as the raw data just slightly massaged. And what I'm showing on top of this is a couple of signal descriptions. Okay? The dark blue is a no GR model. We're just kind of looking at what sort of signal is there correlated in your detectors, but you have no idea that general relativity exists. And then the light blue, the cyan here, is using the full GR model. And what you can see is that they essentially lie on top of each other, which is quite remarkable. This is the first time this has been done. The GR predictions are quite involved, and yet here they are right on top of each other. Okay? So that tells you that they really do seem to be black holes. Another way to say that is if you take the best fit model, this is all for 150914, if you take sort of the best fit model you have from your analysis and you subtract it from the data, you can look at the residuals and you can ask, are the residuals consistent with noise? Or is there any remaining signal there? Using the same sort of analysis I just showed, the unmodeled analysis. And what this plot shows is that the amount of remaining, quote, signal in the data is pretty low SNR and is completely consistent with noise. This is kind of the distribution of noise if you do a same analysis on just random parts of the data nearby. So all of this is, again, a long-winded way to say GR is working. And so just to emphasize, we have this full-blown GR. We do our best fit, we subtract it, there's nothing else left, okay, which tells you GR is fully describing what we're detecting. Now, Dimitrios will probably talk a lot more about other ways to test GR, but I think this is really an emphatic first step for what we're doing. Okay, and then there was a question about, I think Andy had a question about the merger ring down and whether things are consistent. Here, actually, I think maybe this is probably more useful there. There's very weak evidence for ring down. We can talk more about this later if you'd like, but depending on where you start your analysis for the ring down, you can get sort of the one dominant mode, and you do measurements. Everything kind of falls on top of each other, but this is very wide. We don't. This is for 150914. We're not quite there yet to do precision measurements of ring down. Okay, so what have we detected? So let me just talk a little bit about parameter estimation. And again, Scott kind of described how this works. We have models that describe the waveforms as a function of the various interesting parameters, and now you can do fits for all your different events. So I've now color-coded. The dark blue is 150914. You can see the labels on the others, and this is the masses of the black holes in the binary. We have something about the final spin, chi effective, which is a quantity that measures the spin and the orbital arrangement, the orbital angular momentum of the binary, mass ratio, distances. We find out a lot just by analyzing the waveforms. Okay? There are a few interesting things we get to do now. This is a mass distribution. And for people, I've spent some time studying, trying to model these populations. When you first see a plot like this, it blows your mind. This is the actual distribution of masses in the universe, at least measured by these first three events. This I should say this is based on 2.9 events. This is, still in process. This hasn't been, published yet. This is very preliminary, but you can see that we're starting to get some sense of the mass distribution. And this will only get better. This is just a numbers game. As we get more events, we'll measure the mass distribution of these black hole binaries. Okay. All right, another very interesting thing is spins. And so these are spin disk plots. So this is each one, so this is for 150914. The left panel is for the more massive member of the binary. And the way to read this is the length of your line here is your dimensionless spin value. And the direction tells you whether you're aligned with the angular momentum, anti-aligned, or in the plane of the orbital angular momentum. So this up here, if you're at 1 up there, that's your maximally spinning and aligned with the orbital, with the orbit. Okay? And there are a few things you learn immediately. First, not all black holes in the universe are extreme Occur, which is something you might have assumed. There are some people that thought that was a very natural way for black holes to end up. But there's just not much support here at the outer edge. So they're not all extreme Occur. You also learn not all black holes in the universe are Schwarzschild, which might also be shocking, but you can see there's actually very little support right around 0 here. And so you know that there's some spin of the primary in this case. So just from these first 3 events, or 2.9 events, we're already learning very interesting things about spin. Now the details of these spin disk plots get even more interesting in the context of understanding the populations. There was an allusion to this, rates. We're trying to measure the rate of these events. That's very relevant going forward, trying to make projections for what we're going to see, but it's also relevant if you're trying to model these populations astrophysically. We really don't know the rate yet. There are huge uncertainties. You can sort of do essentially Poisson statistics, and you get rough estimates. The numbers we're talking about are on the order of tens per year per cubic gigaparsec. But this, again, it's a numbers game. As we get more, these will narrow, for sure. If we don't see any more, they also narrow, but lower down. OK. So there are a number of other interesting questions. How does the universe make these black holes? A lot of people have talked about how it's quite surprising that we've seen them. I'll just point out that there have been a number of papers that I've been involved with, also with Emanuele, where I don't want to say predicted, that's much too strong, but we argued that a lot of the formation scenarios should produce black holes exactly in this mass ratio. This is something that naturally comes out of stellar evolution, in some models making some assumptions. And I think I'll skip over the detailed models. I mean, this is an example of full evolution where we take 2 stars and we evolve them forward, and we end up with something that looks a lot like 150914. So the main point of this is there's a lot of astrophysics here. So if we measure these things, if we measure the rates, if we measure the mass ratios, if we measure the spins, we're learning about an incredible amount of astrophysics. And that's really part of the goal with LIGO. Okay? I'll also briefly mention, you can ask, can we see these sources? Now, what I mean here is, can we detect them electromagnetically? And you might ask, well, would we expect to? And that's something we're not sure about. I mean, Avi, says we should see them, and maybe we will, but we have to look. This is how you look. So this is just for the very first event ever, and I think this is something that bears remarking on. This is the very first time we turned this on, very first event, and yet within a couple of days, we had an announcement that we'd made a detection. We sent it out to a bunch of EM partners. They did an incredible amount of follow-up. I think that's pretty impressive for the very first time this had been done. A lot of people responded. I'll also mention, I work with Ito. We use dark energy camera to do follow-up. We did a bunch of follow-up. I think we probably did the most extensive optical follow-up of any group. We didn't see anything. But this bodes very well for the future. And there's a lot of interesting science, including the standard siren stuff that comes out of that. The basic problem here is that the localization areas are too big. So that's a bunch of galaxies. This is, Hubble Deep Field compared to the moon. And this is the sort of localization we're talking about. So there are a lot of galaxies in here. It's tough, This is not something that's just going to be totally straightforward. So I'm going to spend just a few slides. I'm sure Matt will talk a lot more about this, but a few slides on the future. And so I'll point out there are 2 LIGOs. Virgo is right now developing quite well. It's going through commissioning, and we're hoping it'll join the network in a couple of months. Then there's Kagra, a Japanese detector that's being built underground, and LIGO India is progressing well as well. So eventually we'll have 5 detectors. Right now we're at 2, and hopefully soon 3. I'm going to actually, I'll just go, there's a whole plan for how this will develop. The bottom line with this plan is we'll have more detectors, we'll have many more events, we'll have much better localization. We're guaranteed to have high SNR events. There were some questions about this. The event rate is unknown, but it's going to be, our detectors are only going to get more sensitive. We detected 2.9 with a less sensitive instrument, so you can assume we're going to detect more, and that guarantees that you have high SNR events, given the way gravitational waves work. There's a fixed distribution, you're guaranteed to have high SNR events, and that means a lot of different things improve. Let me just show one other thing that's relevant for the future, which is the localization. This is what we have so far on the sky. These are huge parts of the sky. But let me just show you what happens if you add Virgo to this network. So in particular, look at the green contours, which are 150914. You add Virgo, that turns into this little dot. Okay, and I should say this slide was made by Leo Singer. This is really a dramatic improvement, and this is why we're particularly excited about the future of multiple detectors. I'll also mention, just because this is work I did with a graduate student, Xinyu Chen, who'll be joining the BHI in the fall. And I think it's quite interesting. What we did is we just did analysis going forward, asking how well will we localize in 3 dimensions. And we showed that for some fraction of the sources, we're going to localize so well that there'll be 1 galaxy in the localization area. So this is to say, you don't need an electromagnetic counterpart. Just the gravitational wave network will tell you exactly where the source is coming from. And there's a lot of interesting astrophysics that you can do with this. You can do the whole standard siren game, but you can also, you'll learn about the environments of the host galaxies. You'll learn a lot about formation, metallicity. There are a bunch of things you can do if you actually have unique counterparts. So that's something for the future. I'll also mention, I think this is just quite interesting, you can do quite a bit with the spins. There's a lot of interest in spins. You might notice here that all the final spins of the systems we've detected are about 0.7. You might ask, why is that? Is that just pure chance? And in a recent paper, and Emanuele has also done a paper on a very similar topic, we showed that actually, no, this is what you expect. When you have a binary system, binary black hole system, anywhere near equal mass, there's a lot of orbital angular momentum. And so the final black hole is inevitably spinning. And in fact, the distribution of the final spins is pretty universal. You can adjust the mass ratio, you can adjust the initial spins. You always end up with the final black hole that's spinning around 0.7. And what that lets you do is you can now say, okay, just based on the LIGO data, forget all the theory, how you think these are formed, just based on the LIGO data, can you figure out whether the individual black holes in the binaries were made from even smaller black holes? Just as a question. And the answer is yeah. If they were made from smaller black holes, they'd be spinning at about 0.7. If you can put pressure on that, rule that out with your observations, then you've shown that the individual black holes probably did not form from smaller black holes, and then maybe they formed from stellar collapse, which is what everyone believes. But it's worth kind of thinking about this. And I'll point out that there's been a lot of excitement about primordial black holes. Those would almost certainly generate a bunch of mergers early on, and so the individual black holes in the black hole binaries, the component black holes, would have been spinning, and they're not. Okay, so there's this is just the sort of science that this is opening up. Again, this is just a few events. Okay, so I'll just end with this slide. Where are we headed? Okay, tens to hundreds of detections in the near future. We'll have all sorts of distributions. We're going to constrain the way these black holes are made, and then there'll be a lot more interesting things having to do with the host galaxies, their stochastic background. We'll do tests of gravity. Maybe we'll detect supernova. There's a lot. The future is very, very bright, loud, however you like to say it. And of course, the things we're most excited about are the surprises. Okay. Yeah.
If I read your diagram correctly, the spins of the black holes were not aligned with the orbit.
So,
If that's the case,
which diagram?
if I read that correctly,
Yeah.
now, if it was normal stellar evolution of a binary system, would you not have expected that the spins would be aligned to the orbit? And does that not imply that there is some other path other than normal stellar evolution?
Right. So I guess there are two answers to that. One is it could be normal stellar evolution, but in a high-density environment like a cluster, and then the spins, you get lots of exchanges, so the spins are random, not aligned. So that's one.
Not easy to do.
Some would argue that, but we can talk about that. And the other is, even in the normal scenario, you have kicks. For example, when the first black hole forms, it can have a kick. And depending on the magnitude of that kick, that will misalign the spins. And the question is, can it misalign it sufficiently? We don't know. We actually measure the alignment very poorly so far. So that's one issue. And the other thing is, if you have all of these are consistent with small spins, and if they're misaligned, they could be in the plane, for example, but small, and that's completely consistent in the field models as well. So it's complicated. Where it gets, I think, very interesting is if they're misaligned. If you have, as in anti-aligned. So if you have all your spins upside down compared to the orbital angular momentum, then I think it's very hard to do that with any model except for cluster models. And so, but that's, again, a statistics game. We'll have to see. The spin alignment is something we measure very poorly. We measure well the aligned component, but the in-plane component we just don't measure very well.
From the length of your answer, I conclude that yes, you would have expected them to align, but you can explain away the fact that they're not.
Yeah, no, I think it's just, you should take it as it's a very interesting topic.
Are we very quick? Deirdre, can you set up? Yeah, you're running out of time.
So I just wanted to refer to your last bullet. Nature is often more imaginative than we are, and we should not take it for granted that we sort of imagine the type of sources that we see, that there is nothing really unusual coming, right? Because LIGO would have detected if there was some cosmic string or some other type of source out there.
Yeah, that's right. I mean, I think we're all most excited about exactly those. I think it is nice to see that the bursts, so we have searches which are unmodeled, and that those are clearly working. Because, in fact, some of these were first detected through the burst pipelines rather than the model pipelines. So we'll see. We'll see.
Thanks, Dan.
So I'm going to, again, in the same vein, there's a suspicious amount of black holes being discussed here at the Black Hole Institute. But now I'm going to look at it from the point of view of someone who works on the full Einstein theory as a numerical relativist. So what can we learn? What will we learn about black holes coming from the fact that we now see the merger, which means we're really looking at an aspect of the theory that's nonlinear, which I think is one of the most exciting things we're getting out of these detections. So my goal is, as we look at these plots, I think by now everyone can take a test on what we detected, our black hole binaries. So I will tell you a little bit how what numerical relativity is and how it was used to confirm these gravitational wave detections, especially because we're talking about the merger of the binary black holes and what that means, and how it interpreted the source parameters. And I think for this audience, we've learned that some of the most exciting topics are in that end. How do we test general relativity, or what might we learn, and what's next? What could we speculate that we could be going in this direction? So I think for me, the most exciting part is about what we can learn next. Over the last couple years, I think my group and I, we were obsessed with learning enough about the detector and understanding the data analysis, and then suddenly you have detections, and lo and behold, they were actually of the merging of two black holes, and then suddenly we can ask ourselves, what can those gravitational waves teach us about the central engine? And that central engine here are two black holes merging. The nonlinear aspects of general relativity are inescapable. So what will the merger reveal to us about gravity? And maybe we don't know the answer right now, but we certainly have a beautiful opportunity to go back to the drawing board of the theory and say, what could we learn about the dynamics of the horizons, what's happening in the merger, given that we sit there now with the merger in our hands? And it will just get better and better in time as the sensitivity of the detectors increases. So I think this is more of a what we could do thinking ahead about as the detectors get better. So this picture, I should just point out, will set up the story that you've heard most of it, right? Everyone, we've been talking about the in-spiral merger and ring down of two black holes. Most of my focus is here at this merger part because that's where you need the full solution of Einstein's equations to study. And here's what the horizons look like. If you do a numerical relativity simulation, that means you're going to solve Einstein's equations fully numerically, so no approximations. So the two-body problem becomes very challenging. And it's made a little more challenging because there's a singularity sitting at the center of those black holes that we have to deal with on the computer. And so if you look at this is a plot of the energy radiated in this scale-free time. So pick your favorite mass and multiply. And we see here the merger of the two black holes. That's given by this outermost horizon showing up in the two individual horizons, and then it rings down. You can see the amazing amount of energy that's being radiated right at that moment as the black holes merge. So I want to explore that region a little bit more. So I can't help it. I love this quote, so I always show it. So I'm not going to show you too much on numerical relativity because it's not as bad as Luc Blanchet's equations because we don't write them all down. We let the computer solve it. But still, no one wants to see the code. So I usually just quote Misner because I love it. I love the fact that in GR conferences of old, instead of filming us, which is scary, they just took notes. I prefer that somehow. And so Misner talked about the computing machine better than anything we have now, and many programmers and lots of money, still true. And that the programmer will shoot himself or the machine will blow up, because that's how hard the problem was going to be. No one died in the pursuit of numerical relativity, I'm happy to report. And there's been some success, right? So in 2005, Franz Pretorius, famously in a kind of one-man effort, was the first person to successfully merge two black holes on a computer. And very soon after, which I think if we have some sociologists in the audience, you know, it's interesting that once something can happen once, then the field opens and all of a sudden everyone can do it. So within a month, you know, you have just about everyone doing numerical relativity around the world successfully reproducing the effort. So in 2006, we had a completely different methodology than used by Franz Pretorius called moving punctures. And a month after that, all the other groups could do it as well. So what were the keys to this after it took from 1957, called the Holy Grail by Tchaikovsky and Shapiro in the 80s, really horrible, tough challenge, and it was because you have a black hole singularity sitting there, even though you have no other matter. So as Scott talked about Chandrasekhar's quote, there is something so beautiful about a black hole, right? It's got mass and spin. We even ignore charge. And yet, put two of them together and we couldn't solve it for a very long time. And it's that combination of the singularity and our ability to do computing. And the truth is, we had to be smart mathematically to write the formulation down in a way that was controllable, but also we had to have big enough computers to resolve the singularity. And that we kind of forget sometimes. So I think there was a time where we had to get the computers good enough so we could successfully solve the problem. And then many methods worked. So I'm not really going to go into details of all that numerical relativity. Instead, I'm going to talk about what do we need from us, them, so we can move forward in this brave gravitational wave astronomy where black hole mergers may become routine. And what we need from numerical relativity are the gravitational waveforms, because that is a tool in the toolbox of building up all of these famous template banks that LIGO and the future detectors will use to figure out what source we have found. So there are 3 public catalogs currently available from our group, SXS and RAT. They're constantly populating waveforms in those catalogs, so we probably have about over 1,000 publicly available at the moment. These plots are just to give you a sense of the parameters that have to be covered. So the problem with this work is that for each realization of the parameters of the black holes, we solve the equations once, we get a waveform out. So each one of these cute little dots is some realization of parameters, and it can take weeks to do one of them. Sometimes days, but sometimes weeks, depending on how far apart the black holes are, how many orbits you have to recover, how long, and how much accuracy you need. So it's a little slow going. It's not very sexy work, right? You just slog in, do another code, try to figure out where do we need the next waveform. That's a huge industry in and of itself. And so we slowly populate both the initial spin vectors, that's 6 parameters, the 2 black holes, that's 8. Is there a centricity? What else is happening? How much precession do we have? And we slowly populate this space. The nice thing is when we do this, we sort of get for free the final mass and spin of the black hole. So we get out recoil, more information than just the waveform, the luminosity of the source, et cetera. All this will come out from these waveforms. And then what you do with them is a question. So this is my cartoon of what we do with them. So sorry. So the amount of work that goes on here is really amazing. To put it in a cartoon is funny. But this is the way I see data analysis. Don't tell anyone, Matt. No, I'm just kidding. I see it as a noisy room. So it's a hard problem because these detectors are sitting on the ground. It's noisy. It's that simple. So this is a cartoon of someone trying to hear their friend speak in a room of very, very noisy sounds. So in some sense, the best way to approach if these sources are general relativity solutions, if we can imagine the sources are, as Scott and Dan were saying, then we can actually solve the problem and have the theoretical map in our hand to compare to all the signals. And that's what people do. So this plot from Bonanno and Satya is about what we use in theory to predict these waveforms. I've been focusing down here, because that's what I do, in numerical relativity, where we cover the merger of the 2 black holes or neutron stars. So this is mass ratio, and this is separation. If the black holes are far enough apart, you can use post-Newtonian theory, which is a few steps away from what Scott was talking about. And there you can get the in-spiral, that chirp mass he was talking about. You get a lot of the information before the black holes get so close together. And basically before their speed is so fast that you can't use this approximation anymore. And the flip side of that, something Scott also mentioned, you can use perturbation theory if you have high mass ratio, and you can basically treat the system like a black hole with something orbiting it that's small. And there are methods that kind of combine all of these, that use the numerical relativity waveforms, use post-Newtonian information, use all this information to create a model of the full signal. There's 2 things that do that. This is effective one body, so it fits the final parameters to the numerical relativity waveforms. The second one is called phenomenological waveform. It does the same. So to cover the full space of in-spiral merger and ring down, it fits to numerical relativity. And I added this 3rd bullet just because GW 150914 was special, and it was so loud, we actually could compare directly to numerical relativity without going through a model as well. And the name of the game here is that if we just use NR waveforms, we would have this discrete space because we take a set of parameters, we make it run, we put a dot down on the plot. And what you really would like, ideally, is this smooth representation of the parameters kind of completely interpolated between the points such that a detection won't fall through the cracks. And so this is what these models provide us, some speed and this ability to search across. Now, of course, there's caveats. One, we're sort of at the mercy for the sources we've seen, which are really merging black holes, of how far out in the boundaries of the parameter space have we actually produced waveforms to model, and how maybe there's going to be a situation where we miss an event because we haven't modeled it yet, or because general relativity is not completely correct. So we have to be prepared for all of those eventualities. One thing is nice is that because there's also the search, as Daniel mentioned, that doesn't use the models, so we have a chance to catch them. So one of the things that this does is it provides us a map of the initial parameters seen here at the spiral to the rain down. So numerical relativity provides that match of how you might, in fact, there's formulas that literally take the initial mass and spin values, and we just use all the information we've learned from numerical relativity to pop out what types of final mass and spin and recoil you should expect. So this is one of the things that gets used in these detections, since it's really hard to capture ring down. Instead, you'll see people say, well, given our initial parameters, we know where we should be sitting on this final mass and spin plot. So that's something that is nice to have the consistency check. I'm looking forward to the time where we measure enough ring down that we get a harder constraint. So you saw this plot from Dan a second ago, and I'm just going to reiterate it a little bit. You might see it again from Manuel. I don't know how many times you'll see this plot today. But it's interesting. We're here in a black hole conference. Obviously, we all want to know as much as possible about the black hole. And here is this ring down portion we've been kind of obsessing about, because it's one of those ways that you can really say, I know that's a black hole because it rings like a black hole. It has the unique signature that general relativity says it must have. But it's kind of a bugger because it's exponentially damped. That means it's not going to be easy to detect. You need a lot of signal-to-noise ratio to even get the fundamental first mode, let alone getting the ones that we call higher harmonics that are decaying even faster. So all these millisecond things here is because you have to figure out when you think ring down started. So numerical relativity gives it to us, right? The signal gives it to us, but we don't know exactly when we begin to have this damped exponential, indicative of a ring down. So you take different slices and you check. And then this black line here is from using that formula I just described from numerical relativity for the predictions. And it's consistent with Kerr. Consistency is good. Pretty amazing for the first detection. But it's really hard. So we've been asking ourselves, and other people will talk about this more, what does the future look like? What would it take to actually be able to see these higher modes and start to say, if I see two modes, I can actually tell you, is this Kerr or not, and really test general relativity. So here's an old plot from 2014 from one of my students back then, where he was looking at the higher modes and looking at, like, if you had advanced LIGO versus this dark curve is, I think, the Einstein telescope, what it would take to see higher modes so that you can get more than one. And it's hard. It's challenging because they're exponentially damped. So there's two things that I'm going to say here that are a little more speculative, but that I would like to work on in the coming months. One is the boring part, which is I think that if we really want to test general relativity, we can't leave any physics lying undone in these models. So if we want to probe whether or not general relativity is correct, we're going to have all the details right. Precession, eccentricity, higher order modes, which we haven't talked about, which just means getting all the energy radiated together. So this part, I think, is crucial in order to really properly test GR. We really are going to have to make sure we haven't ignored any physics. The second thing is that I think we have an opportunity here. This part is pure ring down. But we have the merger in band. We know how the theory behaves there. If we can start making better predictions about how the merger indicates what the ring down will look like, it might be easier to get at some of the physics of merger because it's got such a high energy radiated. It'll have a higher SNR. This is even more speculative, but motivated by Abhay Ashtekar, who was here at the Black Hole Initiative, I think last week, giving a talk. This came from one of his slides. And that is to use gravitational waves to probe the horizon. So Scott talked about the multiples of the horizon. This is an initiative that Abhay is working on with collaborators where you try to connect the multiples of the horizon itself. So remember, the horizons are really what's going to be causing or generating a lot of the really interesting physics. So if we can get at the horizon, if we could understand how these dynamic horizons, so this plot is showing you how when the black holes merge and start to ring down and finally get to that Kerr state, which is this boring and final place where we have really good stationarity theorems and we know what's happening, we know how the no-hair theorem applies. As we approach it, we're very dynamic. So we have dynamical horizons in this regime. If we can understand how the horizon loses its hair in this region, we might be able to learn something new about the black holes. And if we can correlate that outgoing radiation that we pick up with LIGO and other detectors to what's happening at the horizon itself, then we'll have a way of connecting radiation to the local properties of the black hole merger. So that's, to me, exciting and sort of going back to the drawing board of the theory and trying to understand what's happening. This plot is just to show you what the horizons look like. These are apparent horizons. They're a local definition of a horizon that we use in numerical relativity. It's an unequal mass binary that merging in the end. And you can just see how dynamic those things are. So there's a lot of interesting physics here. And if we can get at them by using observations, I think it will be a very exciting future. So the challenges ahead, I think we've really just begun to explore strong gravity in the universe. And here it's sort of the opposite of what Daniel was talking about. Instead of being a numbers game that we need a lot of statistics, we need some really high SNR detections to get at the ring-down modes, to look at all this interesting nonlinear physics. I think understanding GR in this regime is necessary to do tests because we have to know all the physics we do know from GR before we can probe how it might be wrong. And it might be a little speculative, but I think it's interesting to look at this as an opportunity to explore black hole horizons from gravitational radiation. So exciting times ahead. Thank you. Hi.
That's a great talk, thanks. So when we think about imaging black holes, what people say is that, yes, you might be able to see a shadow or something, but it could be induced by a gravistar or a boson star. Are we beyond that with LIGO? Are there any other exotic constructs that can mimic these signals? Are you worried about that at all, or has that been put to bed for these mass black holes?
I think, and maybe other people in the audience want to speak up, but I don't think we've quite put it to bed. So it's consistent with Kerr. I think you need to see more than one ring-down mode to say that's an Einstein Kerr black hole signature. It can't be a boson star. It can't be a gravistar. So that's where I say we just need a little bit more SNR because these ring-downs are tough because they're exponentially decaying right as the noise floor picks up. So for me to be like, there's no shadow of a doubt that this is a general relativity Einstein Kerr black hole, you need more than what we've seen so far. So we have consistency, but not, put it to bed, I think. Anyone want to jump in on that? I feel like Daniel wants to jump in on that. I share my talk time.
I mean, if you had a really compelling alternate model, I mean, saying it's a gravistar is fine, but you really have to write the equations out. It has to be dynamical. If you had something like that, then we could start asking questions about whether we can differentiate. I claim we don't really have that yet. So all we can say is, well, GR seems to describe what we have. I'm not sure where else to go. I mean, we should still look and keep, but the premise seems to be we have these alternatives that we can really rule out. It's hard to do that.
It's almost worse than that because even in alternate theories, which I didn't talk about, it's really hard to do the merger for an alternate theory because you have to solve each equation one at a time, right? We don't have post-Newtonian, it's a bit easier because you can parameterize the way you might deviate from GR. But if you're doing the full nonlinear part, we're literally solving these equations one at a time. So that makes it even more challenging. Did you want? No, you're going to come next.
So maybe you should set up, Matt. I have a question. So you talked about these two different approaches, the effective one-body and phenom, right? Both of which are trying to combine the three different regimes. Have they been cross-compared to see how well they agree?
So these models actually are both used. If you grab the original detection paper, those are the two models that are sitting there, and you're looking at the plot. They've all been compared with each other with numerical relativity, compared to numerical relativity without using the runs that they fit to, so it's all been very well compared within the boundary of where they're applicable, right? They're not applicable across the entire parameter space, but where they've been tested, everything's looking good.
So I'm going to try to pick up where Dan left off here and talk a little bit about the future and where we're going with these things. The title From Nothing to Everything is really supposed to say that we started out not very long ago with 0 binary black holes detected. And I'll tell you in this talk how we go from that to detecting all of the mergers which happen in the universe. So right now, we're looking at low redshift binary black holes. And the future of ground-based detectors takes us out to higher redshift, sort of as a function of time. So you see these sensitivity curves. This is initial LIGO here in green, and I don't know if anyone actually said what these axes are. So this is the frequency in hertz. This is our strain. And all of them move down and to the left with time. So moving down is really just saying the detectors are getting more sensitive, and to the left means we're moving to lower frequency. So the progression from initial LIGO to advanced LIGO, from the green to the red, follows this sort of down and to the left. And that takes us closer and closer to our sources. The way that this first step happened was really we tore everything out of the vacuum system for LIGO and stuck in new isolation systems, new mirrors, got a big laser, sort of everything got bigger and better. And that's how we moved from the green to the red on that plot. The truth is that we still have a ways to go. And we were surprised, I would say I was surprised, personally speaking, to have detected anything in the first observing run with advanced LIGO. That was just the first observing run. So we have more laser power that we can get in these detectors. The sensitivity can be improved by a factor of 2 or 3. And that means that we'll be detecting sources at a higher rate as we move along with advanced LIGO. That's without making any real changes to the design. So what I'm trying to say is advanced LIGO is really not advanced LIGO yet. This was just the first observing run. We have a ways to go. So that is between the red, where we are now, at least roughly speaking, and the blue, is a factor of 2 or 3. Okay, that's problems for people like me who work on the detector, just getting more photons in. And the reason why this is so interesting to us is because, I mean, you say, okay, better SNR, that's fine, but here's a binary black hole system. Roughly, this would be where the frequency domain plot, you saw the real version of this earlier, would be for something at 400 megaparsecs. That's like our first detection. SNR is good, that just means it's well above that red curve. And then here at the end it goes splat. If you put the same system at 4 gigaparsecs, we wouldn't detect it with the current detectors. But with the design sensitivity, that would be just at the edge of the kind of thing we could detect. So instrumentalists tend to talk about the range of a detector. And the range is the distance at which, it's kind of like the median distance at which we could detect sources. And this one would be a little bit beyond the range, out towards what we call the horizon. So at the maximum distance so we could possibly detect something would be 4 gigaparsecs. It turns out that unlike electromagnetic observatories, we win with the amplitude. So if we double our sensitivity, that's if we move the sensitivity curve down by a factor of 2, we can see things at twice the distance. So our range increases by 2. And if you put that in terms of volume, you go from something like this for initial LIGO, with some, this is the Virgo cluster, sort of local galaxies, to something like this for advanced LIGO, right? So we're winning with the cube of the range. The volume of our detectable space is growing very quickly. So if we double, just a double or a little bit more than that, our sensitivity, we double the range, we get a factor of 10 in event rate. So again, our progress is moving this way. As we move just from here to here, we can go up at roughly a factor of 10 in terms of the rate at which we detect sources. Dan also mentioned the other kind of progress that we'll be making as we go along, and that is we'll be adding more detectors to the network. So right now we have just these 2 detectors operating. Soon Virgo should come online, and the Japanese Kaga detector, and eventually LIGO India. So the other progress which will be happening over the years will be the addition of more and more detectors. All right. The second half of this talk is really more speculative, and hopefully something you haven't heard too many times already. So what I do at MIT is think about where we're going next. And this was the light blue curve that I didn't mention on the previous plots. How do we go beyond advanced LIGO? How do we make these things better? And what do we get when we do make them better? So we can imagine a whole decades worth of future in this field. Advanced LIGO is up here. And if you do the best that you could possibly do in that facility at 4 kilometers, you end up something like this. It's about a factor of 3 better than advanced LIGO, roughly speaking. If you're willing to build a new detector, like the Einstein telescope you heard named here is in pink, you can get somewhat better than that. At 10 kilometers with a LIGO-like detector, you're here, 20, you're there, 40, you could be down here. Right? So as we move to the future, we imagine building new detectors, and there's some significant efforts now going into designing and getting funding for conceptual design studies of new detectors. This is a detector concept called Cosmic Explorer, which I've been working on. I'm not going to talk about how the detector works. I guess most people here don't really care. But I'll try to talk a little bit about what we get out of this. So I also won't get into Emanuele's paper here at all, except to pick out the part that I found most interesting, which had nothing to do with general relativity. But this paper takes all of the curves we've published. This was a brave move. Like we've put out lots of sensitivity curves. And again, you see the progression here is down and to the left. So as we move from the current detectors to Cosmic Explorer, which is the CE thing here, right? We're moving down, better sensitivity, to the left, lower frequency. This is roughly 2 decades worth of progress as we expect to cover that region. So in the next 2 decades, as we move through various detector generations, we'll go from detecting a few events, here we are right now, this is events per year, and we're at a few events per year. And we move up the various detector generations. This is the advanced LIGO design, right? We could be at tens of events per year, and you move along, and as you get to something about 2 decades out, you're at something like several 10 to the 5, almost 10 to the 6 events per year for binary black hole systems. That's basically everything in the universe, right? We go from detecting essentially nothing just before a 1 here to really detecting everything that's out there. This number isn't really determined by the sensitivity of our detectors anymore. It's determined by how often these things happen in the universe. If you're worried about quasi-normal modes, I encourage you to read this paper. This curve I took just to mean the signals which come in with a high enough SNR that you can say something interesting about the quasi-normal modes. Again, at the end, with future detectors, a couple generations out, or a couple decades out rather, 1 generation out, we're at something like thousands of these events per year. Right? We won't be in the small number statistics game for very long. And even just as we move to advanced LIGO design, we won't be anymore in the regime in which we wait months between detections. If you take future detectors and you take that rate of several 10 to the 5, we're talking about a detection every 15 minutes, roughly, so quite rapid. If you wonder where these things are coming from, honestly, I can't tell you because it depends on things that astrophysicists know and I don't. But if we get the best guess, the answer is most of our sources will come from Z of a few, 2, 3, 4, something like that. But we'll have some out here at redshift larger than 10. And I would argue that depending on where you think these black holes are coming from, they could be at even higher redshift. So from an instrumentalist point of view, we can quantify what's the largest distance to which we could detect a given source. And that's shown with these sort of dark curves here. So for the Cosmic Explorer detector, the one I've been working on, that curve reaches out to a Z of 100 for things where you have a total mass of the system of 10. Right? I don't really think there's anything out there, but if there is, we'll detect them, at least a few of them. Right? Very high redshifts are available. So really, it's not, when you have detectors that are this sensitive, it's not about pushing to larger distances. It's more about getting good coverage and high SNR of everything where we think there might be real signals in here. So what's the message? The message is that once we get to advanced LIGO sensitivity, we're not there yet. We could be at roughly 1 per week as an event rate. These will probably mostly be binary black hole systems. We shouldn't forget about neutron stars, but I guess here that's not really the point. Mostly these systems will be at a redshift less than 1. Near-term upgrades. So this is, you might have heard of squeezed light, or probably not coding thermal noise, but the things that I worry about. This could get us a factor of 2, maybe a factor of 3 in the current facility. And this would take us from roughly 1 per week to roughly 1 per day. When we want to take the next big step forward, we'll need to build a new facility. If we do that, next generation detectors will be taking us out to high redshift, right? And we'll be detecting essentially all of these compact binary coalescences in the universe. That's what I've got. Thank you.
So given that gravitational wave astronomy is no different from normal astronomy, and deeper is better than broader, what is the most useful investment of resources in the field? Should we be spending money building better detectors or improving existing detectors instead of placing detectors around the world?
Yeah, so I think that it's a very good question. I think that the two things are happening here. One is that as we improve current detectors, we're really testing technology that will go into future detectors. So we can't just say, okay, stop doing what all of you are doing. We're going to spend the next decade just building a future detector and have it work. That's not going to happen. So we kind of need the current detectors as a way to develop our technology. That's part of it. The other part of what's going on is when you have two detectors, you can, if you have one detector, you can detect something, but you might not believe it, right? If you have two detectors, you get this coincidence, which makes the signals statistically much more believable. When you go to 3 detectors, you now have good sky localization, relatively good. Good for us, but anyway. When you go to 4, I think the main thing you get at 4 detectors is you have a little bit of redundancy. Now, if one of them goes down, you still have a 3-detector network operating. And I think that's the main feature of 4 detectors. Beyond 4, I'm not sure what the utility is anymore, right? We're a long ways from having 4 good detectors running. So I think, if we were talking about the 6th or the 10th detector, there probably isn't a lot to gain there, right? But up to 4 detectors, I think you're really still winning. The duty cycle shouldn't be ignored because if you have each detector operating with, say, 70 or 80% duty cycle, and you need all 3 of them running to have good localization, you should take that 0.8 and cube it. So your duty cycle will suffer. If one of them can be down because you have 4, then you get much better time with 3.
When you said we'd see everything in the universe, you meant in some restricted mass and redshift range? What did you mean by that exactly?
I think this plot tells you exactly what I meant by that. So the mass, this is the total mass of the system that I'm talking about. So these are binary neutron stars, total mass around 3. Neutron star black hole systems, binary black hole systems, I don't know, maybe there's things up here, I'm not really sure. And out to a redshift of sort of 10, we get from here to there in mass range. So these are ground-based detectors, right? And they're covering up to a few hundred total mass and down to a few. And out to about as far as we think there are stars, right? If you want to go farther up, past 100, then you need a space-based detector like LISA. That LISA mission will basically pick up where the ground-based detectors leave off.
Matt, so could you explain why the detector peak is redshift 3?
Oh, that has nothing to do with the detector.
Okay.
And once again, this is something of which I'm relatively ignorant. That's just star
Is
formation
it just the
rate.
sources?
Yeah, that's just
Okay,
sources.
so the source
So
peak,
it
the
comes
star
down
formation
to,
rate, okay.
so SFR is one thing. The other thing is really just, if you look at where most of the universe is, it's at redshift of a few. When you go to higher redshifts, there's not a lot of time volume product left.
So, Matt, in this idealized future where you're getting signals every few minutes, 15 minutes, I think you said, are you concerned about noise overlap from so many signals? I mean, will there be an issue of separating, which I think Scott brought up earlier, the different individual sources?
Scott hasn't read our most recent paper. It looks like it's not an issue. We could do a real mock data challenge like was done for the LISA mission where you stick in a bunch of signals and see how they overlap. Roughly speaking, it's easy because you can say everything that we get will be fairly high SNR and relatively easy to subtract. And if you subtract all of the sources you detect with high SNR, you're not left with much. But even the simpler explanation is that these signals generally don't last for 10 or 15 minutes. Most of the signal is in the last minute or so, and they don't tend to overlap.
So just another quick question. Between 01 and 02, did the noise curve come down? Maybe you mentioned this at high or low frequency. Did it come down at all?
I sort of specifically didn't talk about that. So in Livingston, the noise got much better. So we can see that there's clearly a way to make progress. The effort at Hanford was mainly focused on turning up the laser power, and we succeeded in turning up the laser power. We did not succeed in improving the sensitivity of the instrument. We think we know why that's true now, and in fact, the reason why the detectors are going down for 2 weeks right now is to go in and clean one of the mirrors at Hanford. We guess this might all come down to a little bit of schmutz that was stuck to one of the optics. So anyway, technical problems prevented us from increasing the laser power at Hanford. So from the experience in Louisiana, we can say that clearly, there is room for progress. We made some progress there. The low frequency sensitivity in Louisiana got much better. Hanford was exploring high power, but in the end, we had to really just roll back to what we had in 01 in Hanford. So it maintained essentially the same sensitivity.
I have a question. So when you were talking about this future, going up to 10 kilometers, 20 kilometer arm lengths, is there a particular challenge in going to longer arms? It seems to me like an engineering, civil engineering problem. Why not just go directly to 20 or 50 or 100 or whatever, to get the sensitivity?
Okay, so there are two answers. One is that more than about 40 starts to not be useful, and that's just determined by the round trip time of light in the arms. When that time becomes comparable to the signal frequency you want, you're not winning anymore. So more than about 40 kilometers starts to not be useful. Between 4 kilometers and 40 kilometers, I think it's dirt and plumbing. It's really just that. And if you have $1 billion to give me, I will start building right now. I mean, really, it's money. That's it. So we're working on it.
It costs so much more to dig a 20-kilometer hole compared to 10? Is that what you're saying?
Yeah. It costs much more.
Just the...
It's actually even worse than that. I mean, it's 10 times more tube. So you have the fixed costs associated with the detector, which is roughly the same. You have 10 times more arm length, but the excavation you have to do is getting worse because of the curvature of the Earth. And it's not, let's say the scaling gets really bad as you go past about 40 kilometers just in terms of cost, because you have to start necessarily tunneling, and that's very expensive.
Yeah,
Just maybe a quick question. So LISA is being contemplated, and that has huge baselines in space. Can you just piggyback on that and do a LIGO in space that has maybe 50-kilometer baselines? Because you don't have to dig anything. I mean, you got to get stuff up there, but has anyone thought about just doing a LIGO in space?
Sure, it's a great question. So it turns out that in terms of strange sensitivity, there are a few sweet spots available in parameter space detectors. Ground-based detectors hit one sweet spot in which what we're doing is we have resonant arm cavities, so we have a resonant interferometer in which we can pump a tremendous amount of power into an instrument in which we basically keep track of all of the photons. We keep track of all the light in these detectors. Very low loss type system. And the largest you can do that, I mean, basically you have to do it on the ground to make that work. As soon as you go to space, you're dealing with systems in which you can't afford to launch multiple meter size mirrors, which then give you some high finesse cavity to control. The way that the LISA type mission works is it's really more of a Michelson type interferometer, and the spacecraft are moving one with respect to the other with significant velocity. So you can't have a resonant cavity operating there. They're really counting fringes in that detector, and that pushes them necessarily to a much lower displacement sensitivity. But then if you make the thing big enough, your strange sensitivity can be good. So there's a sweet spot for ground-based detectors, which is in this kind of tens to 100 or tens to kilohertz kind of region, in which we keep track of all the photons. There's another sweet spot in space-type missions, where you say, my displacement sensitivity is orders of magnitude worse than on the ground, because I'm losing a lot of my photons. Fine, I'll just make it orders of magnitude bigger. That pushes you down lower in frequency and gives you a LISA mission. In between is actually very hard to operate. So there have been mission proposals in between those two spots. One of them is Desaigo from the Japanese, where they're proposing resonant cavities in space. It looks insane. It's very, very, very hard and very expensive. The next sweet spot is nanohertz, where you do it with pulsars. And there you've moved from an interferometric measurement to a timing measurement. And again, making that step from interferometric to timing costs you orders of magnitude in terms of your displacement sensitivity. But again, you get orders of magnitude in terms of the size, pushing you down in frequency. So as far as I can tell, from having to try to find other solutions, it seems like there are really these three sweet spots available.